Hello everyone. Today we want to solve an interesting algebraic equation. Let's consider the following problem. Let x, y, and z be positive integers such that the polynomial xyz plus xy, plus xz, plus yz, plus x, plus y, plus z equals 104. Our goal is to find the value of the sum, x plus y plus z. This is a nice problem. This kind of question often appears in Math Olympiads. Let's see how we can solve this problem by using basic algebraic techniques. Thank you for viewing this video. Please like the video, and subscribe to our channel if you have not yet done so.
Okay. Let's see how we can approach this problem. The first thing we should do is to try to simplify the expression by factorizing. I group these terms carefully and highlight the common factors I want to factor out. So the term xyz is grouped with the term xy, then the term yz is grouped with y, and then the term zx is grouped with z. We finally have one remaining term x which is left alone. Now that we have grouped the terms properly, we can factorize those grouped terms. We have x times the quantity yz plus y, and y times the quantity z plus 1, z times the quantity x plus 1, and the remaining term x. We see that we can still factorize the first term because the quantities yz plus y have a common factor which is y. Therefore, we factor y out and obtain the quantity x times y times the expression z plus 1. As a matter of fact, the overall expression is xy times the quantity z plus 1, plus y times the quantity z plus 1, plus z times the quantity x plus 1, plus x. It is clear that we have a new common factor in the expression. In fact, we can factor z plus 1 out. We obtain z plus 1 times the quantity xy plus y, plus z times the quantity x plus 1, plus x. It comes that we can also factorize the expression xy plus y. The new expression becomes z plus 1 times y times x plus 1, plus z times x plus 1, plus x. We have to rearrange the whole expression in order to spot new common factors. As we look carefully at this whole expression, it is clear that x plus 1 appears in the first two terms but not in the last term. Usually, when you spot such singularities, it is recommended to tweak the expression so as to have x plus 1 as a common factor in all terms of the polynomial. We do so by just adding 1 to both sides of the equality. This obviously will not change the equality because we are performing the same operation on both sides, but the main benefit of this trick is that now x plus 1 is a common fact of the expression on the left-hand side. We factor x plus 1 out and get x plus 1 times the quantity y times z plus 1, plus z, plus 1. After rearranging everything, it turns out that z plus 1 is also a common factor of the expression y times z plus 1, plus z plus 1. Thus, we go ahead and factor z plus 1 out. In sum, our left-hand side expression is now fully factorized as x plus 1, times z plus 1, times y plus 1. And the right-hand side is 105. It is worth noticing that the number 105 can be decomposed as a product of three prime numbers, 3, 5, and 7. And the prime factorization of any number is unique. Because of this uniqueness and the fact that x, y, and z are greater or equal to 1, none of the factors of the left-hand side expression can be equal to 1 or 105. Consequently, Using the fact that x, y, and z are all positive integers, without loss of generality we can equate each factor on the left-hand side with one of the prime factors of 105. Thus we have x plus 1 equal to 3, y plus 1 equal to 5, and z plus 1 equal to 7. We, therefore, have x equals 2, y equals 4, and z equals 6. Moreover, the sum x plus y plus z equal to 2 plus 4 plus 6, which is equal to 12.
Thanks for watching our video. Please smash the like button and subscribe to our channel if you have not yet done so. We have an extensive collection of mathematical videos covering a wide range of topics.